Thank you very much, Sandy. So, site reliability engineer. How I learned to stop worrying and love the SLOs. An insane deploy on Friday afternoon triggers a path to disaster that a war room full of engineers and managers frantically tries to stop. Who guessed what movie I tried to parody in this title of this presentation? Drop me in the chat. So, good time of the day. My name is Helen Tabunshchyk. I am a software engineer by day and a director of Women Who Code London by, more like 24/7, to be honest. So I'm a software engineer in the site reliability engineering team at Goldman Sachs. And I've been in this SRE role for over 2 years, but have been writing software for high-loaded infrastructure for many years now. While coming from a pure software engineering background before my current role, my passion for creating and running distributed systems at scale has led me to site reliability engineering. Let's review our agenda for today. We are going to briefly touch on introduction to site reliability engineering and why it is important. I'm going to talk about the importance of failures, why site reliability engineering cares about different failure modes. We will also quickly touch on incident management and postmortems. We are going to look into engineering for reliability, considerations you need to think about for building reliable systems. I'm going to talk about metrics, how SRE uses SLOs and other abbreviations to govern release velocity and drive priorities. And key takeaways, summary of the talk. I hope we are going to have some time for Q&A. I would be more than happy to answer your questions. Dr. Strangelove. Yes, correct, Irina. Thank you. I will be using distributed systems in site reliability terminology in my talk. If you would like to revisit those concepts, there are 2 classical books on SRE written by people who have invented this. I especially recommend the first one, Site Reliability Engineering, written to everyone who works with distributed systems. Doesn't matter whether you would like to work in the site reliability engineers or you would like to stay in pure software engineering, it would still be very beneficial for you. Also, please get your chats ready. I will be asking questions. Now, time for a bedtime story. About a night, some wizards and their battle trolls. One fine day in August 2012, a failure to complete a magic spell correctly by the night's wizards on just one of the kingdom's battle trolls resulted in a massive loss of troops in the battle that day. 450 million losses to be precise, in just a 45-minute battle. These loss caused mass disruptions in the balance of power in the realm, ultimately leading to the downfall of their king and their lands to be absorbed by a rival kingdom. All of this occurred because the wizards did not check if the spell they had cast on the trolls had succeeded, and if the trolls were ready for the battle and on the same team today. One was not. It was one of the largest electronic trading firms. They wrote programs to do algorithmic trading, when you buy low and sell high to make profit. Pretty standard stuff. But failure in a manual process to deploy code, and ultimately the failure to test the final result of the deployment, cost Knight Capital $450 million in trading losses. Many of you have probably heard of Mark Zuckerberg's quote, "Moving fast and breaking things." But, drop in the chat, did you know that he revised his quote in 2014 to "move fast with stable infra"? As we like to emphasize, E in SRE stands for engineering. The name was coined at Google around 15 years ago, when they were massively increasing their scale and needed to change the traditional role of system administrators. SRE is a dedicated team mixed of software engineers, systems engineers, and network engineers. We all can code and get easily bored. This is an important concept. We are going to revisit it. We focus on service reliability and operating at scale. Ben Traynor, one of the founders of SRE at Google, has put it in one sentence. SRE is what happens when you ask a software engineer to design an operations function. You would like the aircraft you're flying on to be reliable, correct? I certainly would. I don't know about you. You'd like extensive investigations to be performed anytime an issue happens, both major and minor, correct? Yeah, see, correct. It's not unreasonable to want a reliable pacemaker or avoiding getting stuck in an elevator. But what about software? Reliability is frequently the most important feature of any product or service, and something that needs to be invested in and worked on at all times, because software systems and operating environment of businesses are constantly evolving. But it's usually there is a but. For many years, there has been a clear separation between dev and ops, with ops extinguishing fires and holding the keys to the production, hence introducing code freezes when there are too many fires. Drop me in the chat how many of you still work in the dev versus ops environment. But businesses need new feature to be shipped. Those pushing developers to deliver faster. Devs would quickly write some code and throw it over the fence, claiming it no longer is their problem. A natural conflict arises. There is a peaceful solution to this problem: site reliability engineering. SREs understand distributed systems and how to ensure products can operate reliably and at scale. SRE complements development teams in ensuring products meet agreed service levels. SRE uses data-driven approach to manage risk versus product release velocity. Murphy's Law, and I love Murphy's Laws, one of Murphy's Laws says, anything that can go wrong will go wrong. To build something fault-tolerant, you must understand the dimensions it might fail in. Failures are inevitable, but repeated failures are not. Treat failures as a learning opportunity. I found this very interesting piece of research. A big study of 7 years of production incidents at Facebook have uncovered curious patterns. While 29% of incidents have inconclusive root causes, which mean that the affected systems are too complex, or they might have little visibility, or it's just an unfortunate turn of events and there is not enough data. Software bugs account for only 12% of incidents. The major reasons for failure are plant maintenance, hardware failures, and misconfiguration. However, you cannot move your product further without performing updates or, well, running it, correct? However, don't forget, all failures are not equal. It really depends on various factors. For instance, time of the day. Let's say if you fail at night, the real impact may be reduced. Partial failure, failure on a single function, not the entire application. It defines the blast radius. Then you have duration of the failure. A quick failure may have a smaller impact or may not. It really depends. And then you always have application complexity. Overly complex systems tend to fail due to complexity and cause cascade failures. When designing a system, keep in mind a principle called KISS, which is an acronym for Keep It Simple, Stupid. And it's a design principle noted by the United States Navy in the 1960s. But again, failures are inevitable. So Netflix has come up in 2011 with a testing framework called Chaos Monkey, which started a new direction in quality assurance called chaos engineering. It tests systems by injecting failures into random components. Chaos Monkey made it possible to test a redundant architecture to verify that a server failure did not noticeably impact customers by regularly killing random instances of a software service. Killing. A similar approach is actually used in Linux kernel, a fuzzing framework that generates random inputs for functions and fishes for bugs. When I was doing my research, I found statistics for 2017, and a fuzzing tool called C-Scholar was finding $200 in Linux per month. Don't know about you, that's impressive. However, sometimes focusing only on known failures can lead to another problem, and that's survivorship bias. It is the logical error of concentrating on the people or things that made it past some selection process and overlooking those that did not, typically because of their lack of visibility. Survivorship bias can lead to overly optimistic beliefs because some failures are ignored, such as when companies that no longer exist are excluded for analysis of financial performance, for instance. However, my favorite example is from the military. During World War II, a statistician called Abraham Wald took survivorship bias into his calculations when considering how to minimize bomber losses to enemy fire. The statistical research group at Columbia University, which Wald was a part of, examined the damage done to aircraft that had returned from missions and recommended adding armor to the areas that showed the least damage, based on his reasoning. This, however, contradicted the US military conclusions. The most hit areas of the plane needed additional armor. Walt noted that the military only considered the aircraft that had survived their missions. Any bombers that had been shot down or otherwise lost had logically also been rendered unavailable for assessment. The holes in the returning aircraft then represented areas where a bomber could take damage and still return home safely. Thus, Walt proposed that the Navy reinforce areas where the returning aircraft were unscathed, since those were the areas that, if hit, would cause the plane to be lost. And now his work is considered seminal in the then nascent discipline of operational research. Let's talk again about failures. Being reactive to failures is a battle eventually lost. Being proactive is the way forward. Asking humans to be more careful next time simply doesn't work. We all make mistakes. We can be bothered with personal worries, or we might simply not know the system good enough. Reliability should not be an afterthought. How does SRE help to resolve those issues? There is really a limit to how much people can remember. So to reduce cognitive load, we must prioritize really important stuff. People develop tolerance to noise, such as to high number of alerts, very quickly, which will inevitably cause issues in production. Site reliability engineering relies on very straightforward fundamentals. First, change is a common reason systems break. So yeah, sometimes you have to slow down the rate of change, but always have your software well tested and released via canaries. Second, if you don't monitor it, you don't care about it. Third, incident management is vital, so you can improve the service long-term and do not repeat the same outages. And last but not least, no heroes. While, to be honest, heroics does happen, we must not rely on it, as it's generally a sign of insufficient engineering put into a system. Operational overload and toil are the enemy. There is a traditional SRE saying that I really like. Hope is not a strategy. Use it when designing your systems if you want to run them at scale. I want to tell you about one of my most favorite examples, the Mars Climate Orbiter. It was a robotic space probe launched by NASA in December 1998. However, in September 1999, communication with the spacecraft was lost as the spacecraft went into orbital insertion due to ground-based computer software, which produced output in non-SI units of pound for seconds instead of the SI units of Newton seconds specified in the contract between NASA and a vendor. So the spacecraft encountered Mars on a trajectory that brought it too close to the planet. And it was either destroyed in the atmosphere or re-entered heliocentric space after leaving Mars' atmosphere. This precise destiny is unknown. However, a curious pattern I have found in literature is that as the spacecraft headed toward Mars, it drifted slightly off course 4 times. And each time, managers made small trajectory adjustments, but they did not investigate the root cause. What is also notable, NASA does not place the responsibility on that vendor for the mission loss. Instead, various officials at NASA have stated that NASA itself was at fault for failing to make the appropriate checks and tests that would have caught the discrepancy. That is a very good example of the SRE-driven approach to handling failures, called Blameless Culture. Many of you probably know about Maslow's hierarchy of needs, a theory in psychology proposed by Abraham Maslow in his 1943 paper, A Theory on Human Motivation. But did you know that SRE has come up with a similar concept? Yes, cool stuff, Stephanie. Okay, so we can characterize the health of a service in much the same way that Abraham Maslow categorizes human needs. From the most basic requirements needed for a system to function as a service at all to the higher levels of function, permitting self-actualization and taking active control of the direction of the service rather than just reactively fighting fires. So the very foundational step is monitoring. Don't drive in the dark. It's dangerous for everyone. Second layer is incident response. SREs don't go on call merely for the sake of it. Rather, on-call support is a tool that we use to achieve our larger mission and remain in touch with how our distributed computing systems actually work and fail. Trust me, if we could find a way to relieve ourselves of carrying a pager, we would. We absolutely would. Now, next step, postmortem. As you can see in the example with Mars Climate Orbiter, uncovering root causes and building a blameless postmortem culture is the first step in understanding what went wrong and what went right, and sometimes where we just got lucky. That also happens. Now, while I'm talking, drop me a line in the chat what this picture with the canary means. Okay, I'm proceeding to the next step. So the next step is testing. Testing and test suites offer some assurance that our software is not making certain classes of errors before it's released to production. Of course, there is no way to cover everything, but let's be reasonable about what we could check or could have checked. Next, release procedures. Use CI/CD and test in different environments. Gradually deploy your changes to detect failures on a fraction of traffic. Next, capacity planning. Always plan for unexpected growths and failures. It is called N+K capacity planning. If you go over capacity, spill into another region, or simply throttle traffic to avoid cascading failures. Back to the canary. Okay, there are two absolutely brilliant answers. One is a yellow canary was used to check for gas leaks. Correct. And I love the other one. Canary literally doing something in the dark. Yes, I absolutely feel like it a lot of times. Okay, so a mining tradition dating back to 1911 of using canaries in coal mines to detect carbon monoxide and other toxic gases before they hurt humans ended only in 1986. Unfortunate. It was replaced with automation, but before that, miners used canaries who are more sensitive to the colorless, odorless carbon monoxide and other poisonous gases than humans as a safety check. If the animal became ill or died, that would give miners a warning to immediately evacuate. In remembrance of those births, we release our software first to a specific set of machines called canaries. If they get unwell, we know it's definitely not safe to roll out the release further. Okay, now we can ensure that we can support fast and safe development, which results in a sophisticated and happy product. Some of the aspects users care about. Availability. Is the service up when I need it? Latency. How long does it take to get what I want? Throughput. Does it work fast enough? And correctness. Did I get what I wanted? To measure these aspects, SREs operate with SLI, SLO, and SLA. Let's take a look what is the difference between those abbreviations. Service level indicator is a measurable unit. For instance, pizza is expected to be delivered in 20 minutes. Service level objective is our goal in meeting the SLI, service level indicator, within a certain fraction of time with some periodicity. So, for instance, well, 9 times out of 10, pizza is delivered within 20 minutes. And service level agreement is a legal agreement. If we fail certain service level objective, then there are certain legal agreements in place to mitigate the outage. Certainly craving pizza. Yeah, that's a good idea. So in our case, we say pizza is expected to be delivered in 20 minutes, 9 times out of 10, or else your next pizza is on us. Let's talk about SLI and warm up your fingers. Drop me in the chat. If we are providing a banking app, what do you think the user would care about? Okay, as a user of a banking app, what would you care about? Is my money still there? Yes, absolutely. So let's translate it into correct balance is displayed, because is my money still there? Probably a security issue. Accuracy, availability, yeah, correct. Can I get my money? Yes. How to find my money balance, how to have securities. Good. Okay, let's summarize in a few points. So SLI for a banking app would be about correct balance is displayed, get the information within a reasonable amount of time. We probably want to get it like within a few seconds, right? Not wait an hour to understand whether I have money. And I wouldn't want to have to retry to get the answer. That will be annoying. Next question for you. Drop in the chat what customer does not care about. There are some aspects that engineers do care about, but customers don't. And those aspects, they should not be considered in SLIs. Yeah, backend. Yeah, any information about backend? Anything else? Disk usage, good. How data is stored, correct. Customers don't care about it. How is the system is built? Absolutely, they don't care about it. Okay, cool. So let's summarize. So for instance, CPU usage, memory usage, or any internal errors. Oh yeah, why isn't it isn't working? Yeah, so those are aspects that are certainly important for the engineers who own this product, but users don't care about it. So it should not be your SLI. So an SLO is a target value or range of values for a service level that is measured by an SLI. Choosing an appropriate SLO is complex. To begin with, you don't always get to choose this value. For instance, for incoming HTTP requests from the outside world to your service, the queries per second metric is essentially determined by the desires of your users, and you cannot really set an SLO for that. On the other hand, you can say that you want the average latency per request to be under 100 milliseconds. Or you can say that you want your service to be available a certain amount of hours per day. Usually, SLOs are measured in the number of nines. Here are some real numbers for a particular amount of nines. And while I'm talking about that, do you think we could get away without extensive automation and planning to meet the lowest of the provided numbers, 99.5? So with SLO 99.5, permitted outage per 28 days, it's just 3 hours, 20 minutes. 3 nines is 40 minutes per month. 5 nines is 24 seconds, which is, yeah, it's very difficult. 5 nines is a very, very rare beast in distributed systems. Okay, I still don't see answers, so I'm going to continue. Okay, back to 99.5. Unlikely. it is unlikely that we could get away without extensive automation to achieve 99.5, because it is a standard in hosting industry that one data center has an assumed SLO of 99.5. So if one data center fails, we must reroute traffic to another one in little more than 3 hours, only one time per month. In reality, manual rerouting too often does not work as intended from the first attempt. So to be on the safe side and to not breach your SLO, I would put automation in place if you want to have 99.5. Now, remember I was talking about code freeze periods ops folks likes to impose. To be fair, we still might have code freezes if we breach our error budget. So for example, service My Little Pony's SLO is to serve all requests for friendship successfully 99.99% each month. This means service My Little Pony's error budget is a failure rate of 0.01%, which means 100% minus 99.99 each month. If an outage causes service My Little Ponies to fail more than 0.01% of the time, then all of its error budget for that month is used up and there is a hold on new releases. Error budgets can also be used to prioritize engineering efforts. Now, once you have defined your SLO and are operating in terms of error budgets, you can plan your future engineering efforts. Some, not all of them, some of those efforts might be load balancing between data centers, load balancing in data centers, handling overload, handling cascading failures, building distributed consensus. Let's start with the global picture. We might have to think about load balancing between data centers. As I mentioned, if you want to have 99.5, you have to think about it. Unfortunately, or fortunately, I'm still unclear on that topic, we are no longer in 1973, when the map of the whole internet, called ARPANET back then, could fit on one sheet of paper. We have to care about DNS, domain name system, and we know how many problems you often get with DNS. If you don't know that yet, trust me, there are many problems. And we have to care about Anycast versus unicast routing. Or maybe we use virtual IPs and have to care about migrating them properly. We might have to think about locality and congestion control. And to do all of that, we usually operate Border Gateway Protocol, aka BGP, with all of its caveats. Any network engineer will have plenty of stories about that. Inside data center, we get another set of problems, which can span easily, not into one presentation, but into a course. So some of those examples. Uneven load, which leads to overpaying for hardware. We might care about different kinds of traffic with nuances this causes. We might have to care about per packet load balancing, stateful or stateless protocols. We quite often get different generations of hardware running in the same data center. And of course, this hardware can hold different load. And sometimes we have to care about locality. For instance, for cache hits and connection affinity, we might simply get DDoS. That's not a pleasant thing. And we definitely have to survive hardware failures, because hardware fails. That's what it's intended to do, sometimes fail. And we also have to provide, frequently we have to provide graceful connection draining to ensure we don't break user experience or break as less as possible when we update our software. Simple round-robin load balancing is too frequently not enough. Sometimes we have to deal with handling overload. For this, we have to build meaningful utilization signals. As I mentioned a few slides ago, queries per second are not always really representative. We might have to care about quotas to prevent applications or users interfering with each other if they share common infrastructure, which is frequently the case. Maybe we have to do throttling and simply drop the extra traffic until we restore to the levels that we can maintain. Or we might have to spill to other data centers, even though they're not the closest ones. Also, we might want to have built-in criticality factor. We might want to consider some traffic be important, more important than other. And we might want to drop one kind of traffic, but not the other. And then we absolutely, I cannot stress enough, absolutely have to ensure we prevent cascading failures by preventing overload. Again, back to meaningful utilization signals and reaction on those utilization signals. Then we have to design systems that do not cause thunder and hurt issues. For instance, dozens or hundreds of instances establishing a new database connection after a mass upgrade. What's going to happen? Yeah, your database is going to stagnate. Next, intelligent caching to minimize cache misses. Integration testing to ensure that we do not introduce regressions. And always having ready at hand the action steps for mitigating such failures as fast as possible. Distinguish resolution and mitigation. When running systems at scale, you must stop it from failing first and foremost. For example, if you suspect the reason of failure is a software bug, your rule of thumb is to revert the upgrade, not investigate and fix the bug itself. You still will do that, but on your own pace. Your immediate goal is to make the system stable again. Another dimension we might have to care about, and that's Kyiv, Ukraine, on the picture, building distributed consensus. Some aspects to explore here are systems with leader election, where we have to have the dedicated decision maker. Or we might want to have leaderless architecture if we can split the decisions and thus avoid bottlenecks per se. We might have to think about quorum, a voting system about results, for instance, on a per-region basis. And we might have to include into our design sophisticated queuing and messaging. Those are all very complex topics and deserve not just one presentation, but maybe a full course on it. There is a question while I was looking, what if the bug was introduced months ago and you only found out because an obscure edge case was reached? Yeah, this happens very, very, very frequently. And still, that would require more extensive investigation. And the rule of thumb in this case is still to see whether there have been any recent changes, maybe some configuration that has triggered this and reverted. If it's not as easily detectable and you cannot relate this to recent changes, then yeah, you have to investigate it more deeply. But that would be a case for the whole room full of engineers and managers frantically trying to stop the disaster. Okay, and many, many, many more efforts. This is not an extensive list of what you might have to care about once you have defined your level of reliability. However, this demonstrates some of the dimensions you might be invited, you might have to invite into your design to accommodate your desired level of service level objectives. Let's summarize what we have talked about today. Reliability is the most important feature. Failures will happen, accepted. Repeated failures should not, however, ideally, unless they're like an hour apart, then you cannot you cannot do anything about it. So next, leverage failure to learn and improve system reliability with postmortems and follow-ups. Next, engineer for reliability, be proactive, versus get busy with firefighting during outages, which means reactive. Have meaningful symptom-based metric with service level indicators. And last but not least, challenge yourself and your team to make continuous improvements and be easily bored. Thank you very much. Now it's time for questions.
That was so great, Helen. Thank you so much. Yeah, anybody that has any questions, just drop them here in the chat. And we've got a few minutes left. to answer those questions. But I like your point at the end where you need to learn from the mistakes, like sit down, understand what happened, and actually learn from them. I think we tend to sometimes get caught up in finger pointing, like who did it and how did this make it there, rather than like, okay, what happened, what's the problem, and let's just try to prevent this in the future.
Yeah, absolutely. SRE cannot exist in a blaming culture. You need to have this safety to acknowledge your mistakes, because otherwise you're not just like, I know that, for instance, I know that I introduced some bug, I know about it, but if there is this blaming culture, I'm not going to tell about it to anyone.
Yes.
So no one is going to be aware of it. And it's not good for business. I see there is a question, are there courses for SRE? I'm sure there are. However, I have not watched any of them. I have read both site reliability engineering books. I do recommend. I can try showing it again. So here. So the first one, site reliability engineering book, I super highly recommend it. I cannot stress enough how much I loved it. I remember reading it and thinking, it makes sense. And I was so happy that finally someone has put together like all of those ideas into a separate discipline. The site reliability workbook is more practical. It's more about properly choosing your SLIs and writing down your SLOs. So it's nice to have, and it's optional. I also loved Brendan Gregg's Systems Performance book. It explains two things. One, how Linux works. And second, how to generally debug issues. It teaches you this mindset, how do I do troubleshooting, especially in stressful environment when like money is at stake or reputation is at stake. So you have to be very fast in trying to understand what happened. And generally follow Brendan Gregg. I think he's really great. Data intensive applications, Martin Kleppmann is also a great book. It's also nice to read. Okay, next question. Would you recommend a backend engineer to be familiar with this area of engineering? I definitely would, because it helps you to understand how your system runs in production. Because what I have seen happening in the past, software engineers would write their software and have zero idea how it works in reality. And then operations folks, they would run the software, they would follow some run books, but they have no idea what's inside and they have troubleshooting, which is not good for anyone, to be honest. That's why I really like this blend that resulted in site reliability engineering. It's not operations, it's not pure software engineering when you just like throw over the fence, throw your product over the fence. It's a nice mixture of both. When software engineers write their stuff, write their infrastructure, and they understand how it performs in real environment. So yeah, even if you don't have SRE culture in your company yet, I hope, it would be still very beneficial for you to read about it. Okay, any tips on how to introduce SRE in a workplace that usually plays the blame game? That is an excellent question. So I actually have some experience in that, and there is this great hierarchy. Yeah, here it is. The hierarchy of product needs. Start with monitoring. So if you try to change too much too soon, it won't result in any good outcomes. What I would do meaningful monitoring and just watch and understand how a service performs. And once you have proper monitoring, and if you have a blaming culture, I'm nearly sure that you will have problems in production, just because it's not sustainable at scale. It is sustainable to a certain extent, but not at a big scale. You introduce proper monitoring, proper observability, and now you understand how your system behaves. And now you see the pitfalls and you see problems, and you are kind of forced to think about it, and you are kind of forced to adopt new mindsets. Okay, thank you. Yeah, any other questions? Thank you, Liz.
All righty then. If we don't have any further questions, just want to thank you again, Helen. Oh, we got another one there. If you want to.
Okay, so there is a question: how to change the mindset in a more reactive environment that has been like that for years? Again, I think it's the same point: have proper observability, because you will be like, this environment will have to acknowledge there are some issues, and this will be, you know, like gentle introduction of site reliability engineering. Because if you blame people directly and say like your approach isn't working, that idea is not going to be accepted, just because people are usually very resistant to criticism. But instead, if you try to back up your point with data, with hard numbers, that's what SREs do. You will have to acknowledge it. It's numbers, it's hard data, it's statistics. And yeah, if you remember any other questions after we finish, feel free to reach out to me. I'm highly accessible via social media. There are links in my Hopin profile on LinkedIn and on Twitter. Feel free to reach out. I'm more than happy to talk to you. I'm more than happy to answer questions.
Wonderful. Thank you so much, Helen. And thanks for everybody that attended this session. I hope you've enjoyed the day so far. Please be sure to check out the rest of the sessions and the booths and the networking, and enjoy the conference. Take care, everyone.
Thank you. Bye.